I'd like to demonstrate some of the more technical aspects of this COP heating circuit. This is the most basic manifestation, and there's an off-the-shelf filter just to cover everything going in and out. We've got a couple of isolation transformers. This one off to the here for the right is for the circuitry with a filter capacitor. This transformer off to the left is charging this bridge and larger cap. The pulsing circuit is dumping some lovely square waves, which we can have a look at when I turn it on, through this television transformer. Television transistor. This is from a CRT screen. They're basically about the highest spec transistor available on the market today, rated for 1500 volts. Go ahead and switch the system on. Hopefully you can hear a slight buzz in the background. And on the scope, this is what we're seeing. Some nice square waves. Pause it and have a look at the spec. As you can see, 20 nanosecond microsecond full time, which is about the most important element here, a beautifully small full time. Very hard to engineer that with basic electronics. You also got the duty cycles. They're running about 10% at about 400 Hertz. You can hear this heating element in the middle vibrating slightly, making some noise as the temperature goes up. Ambient temperature today is about 18.3 degrees, 50% relative humidity. Climbing up slowly. This is the lowest power mode, simply just to demonstrate that it's working. We can do the math on the power consumption of the circuit at the moment, about 150 milliamps at 4 volts. I think you'll find that's just under 1 watt of input power. I also put a little switch in up here, just so I can bump the duty cycle from that 10% up to about 30%. You'll hear it doing a bit more work, sucking a bit more power, and the temperature is going to rise a bit more rapidly. The power is being dumped into it, as I said, from this main power capacitor on the input of the transistor driver. Currently sitting at about 88 volts. However, that's jumped down considerably since I turned the power output up, because there's actually not much power to draw from here. It's quite a low power circuit inherently. So up to about 70 degrees. I might stick it back down to low power again. See, the inputs jump straight up. And this thermometer is only good for 100 degrees, so I'm not going to let it rise too much further. So what we have here basically is a very nicely tuned square wave generator. Most of this can be done completely off the shelf with no difficulty. However, getting it to run nicely is something that is a bit more difficult and does take some experience. But you should be able to see some really truly excellent results with off the shelf equipment, unmodified. I'd imagine you would get at least an efficiency of somewhere between 5 and 10,000, about 500 and 1,000% efficiency. Somewhere between 500 and 1,000% with basic off-the-shelf equipment. This one's currently running about 1,500% efficient. I've got the system to run up to about 2,500% efficiency, so COP25. 25 times more efficient than a typical heater, which are all 100% efficient. So here's the basic setup. This is the first sort of prototype that's been worthy of actually exhibiting. It's fairly neat in appearance and very stable and reliable. Now, looking forward to bigger models, and as soon as I get some funding, I'm going to do just that, because this circuit is suitable for any kind of household appliances that produce heat, and all the way up to commercial. I'd quite like to see it powering all sorts of coal-fired power stations. And really, it's got the potential to power an economy. So, what could fairly be termed a good start. And here's the circuit that it's running on, available at infinitegenerationelectronics.com. Free download right on the front of the website. Have a quick look. A few more stats and a bit more material to be added later on for those who wish to give it a go at home. So, have a nice day.